Winter SBP elevation and parallel TSI-3B patterns, an 11-year study, number 1681, the 11th of June 2026, Gerald C. EclaireMD Foundation, category, Healthy Life. Preface for readers, eat more protein and vegetables. Eat less red meat and processed food. Reduce portions if overweight. Eating a little less will not hurt you, overeating for years will. Exercise daily. Walk at least 7,000 to 8,000 steps. Drink 85 to 100 ounces to 0.5 to 3.0 liters of water daily. Sleep 6 to 7 hours each night. Manage stress. Avoid draining people and unnecessary conflicts. Put your health first. Wealth, fame, and power mean little without health and life. Preface. After my hemorrhagic stroke on June 21, 2025, I spent the following month of July trying to understand what had happened to my own body and reflecting on my long-term health history. I realized that the event was triggered by acute hypertension rather than chronic hypertension. Therefore, I completely changed my strategy for blood pressure monitoring. Beginning on August 1, 2025, after 1 month of recovery, I started measuring my blood pressure approximately 20 to 24 times each day, since my stroke resulted from an acute event. I believe that a daily average blood pressure had limited value for prevention. My goal was to capture transient systolic blood pressure SBP spikes so that I could immediately intervene. Through exercise, emotional relaxation, or deep breathing techniques, such as inhaling for 4 seconds and exhaling for 8 seconds, to bring my blood pressure down before my stroke. I had already been recording my blood pressure once every morning for nearly 15 years. Although these data provided a valuable historical record, I found that the measurements became much more continuous and reliable after 2014. I prefer to work only with data that I personally trust. My philosophy has always been that data should tell its own story. The data must lead to the conclusion. The conclusion should never be invented first and then supported by selectively chosen data. To me, reversing that process is contrary to the spirit of science. As I continued monitoring my post-stroke blood pressure through June 12, 2026, nearly 1 year after the stroke, a clear seasonal pattern emerged. During the colder months, roughly from November through February when I stayed in cooler climates, SBP profile consistently formed an elevated winter plateau. In early March 2026, while staying in Hawaii, I developed the TSI-Stroke risk warning proxy model. Inspired by Newton's law of motion, F equals ma, I defined TSI-Stroke equals glucose 120 times pulse pressure over 45 times SBP 120 times amplify. For my own application, I selected an amplifier of 120 to reflect my more than 30-year history of type 2 diabetes. The resulting TSI curve serves as a practical daily warning proxy for my personal stroke risk. I have found it both convenient and informative in my daily monitoring. To further investigate the relationship between blood pressure and stroke risk, I compared the 90-day moving average of SBP with the 90-day moving average of TSI-Stroke. The statistical correlation coefficient is approximately 20% using 90-day moving average daily data and 17% using 90-day moving average monthly data. These relatively low linear correlations are expected because TSI-Stroke incorporates not only SBP, but also glucose and pulse pressure, both of which vary independently and contribute additional dynamics to the composite index. Nevertheless, the most striking observation is not the numerical correlation but the remarkably similar seasonal topology. Both the SBP curve and the TSI-Stroke curve exhibit a distinct elevated winter plateau, followed by a gradual decline into spring and early summer. This parallel seasonal behavior is clearly visible in both the daily moving average curves and the monthly summaries. This study begins with these direct observations and allows the data to guide the conclusions rather than imposing preconceived assumptions upon them. The principal finding of this study is not the magnitude of the statistical correlation but the consistent appearance of an elevated winter plateau in both SBP and TSI-Stroke, despite relatively low linear correlations. Both trajectories exhibit the same seasonal timing, broad winter peak, and subsequent decline. This suggests that the shared seasonal topology may be physiologically more meaningful than the correlatio and coefficient itself. Abstract. Using more than 11 years of quarterly systolic blood pressure SBP records together with approximately 1 year of post-stroke daily observations, a recurring seasonal pattern becomes apparent. SBP tends to increase during winter for Q1 and decline during spring and summer. When the post-stroke 90-day moving averages of SBP and TSI-3B are Compared, the statistical correlation coefficient is only modest. Nevertheless, visual inspection shows remarkably similar large-scale trajectories. Both variables rise during winter, peak in approximately the same period, and subsequently decline toward late spring. These findings suggest that seasonal environmental effects may influence not only blood pressure, but also the integrated physiological stress represented by TSI-3B. The overall trajectory may therefore contain more useful biological information than point-by-point numerical correlation. Introduction: stroke risk has long been associated with elevated blood pressure, diabetes, aging, and vascular disease. Numerous epidemiological studies have reported increased stroke incidence during colder months. Rather than examining population averages, this study analyzes a single individual with dense longitudinal measurements collected continuously over many years. The objective is to determine whether seasonal changes can be observed directly from the data and whether similar seasonal behavior appears simultaneously in SBP and TSI-3B. To data sets, the analysis consists of two complementary datasets. 1. Quarterly average SBP from 2001 for Q3 through 2026 Q2, representing nearly 12 years of longitudinal observations. 2. Nearly 1 year of post-stroke daily measurements, converted into 90-day moving averages for both SBP and TSI-3B to emphasize long-term physiological trends. Data observations: the quarterly SBP record demonstrates a recurring seasonal rhythm in multiple years. SBP reaches relatively higher values during winter Q4 through Q1 or January through March and declines during spring and summer, although the magnitude varies from year to year. The seasonal cycle remains recognizable throughout the nearly 12-year observation period. The post-stroke data reveal a remarkably similar phenomenon. The 90-day moving average of SBP gradually rises during winter, reaches a broad peak around January through February, and the declines during spring. TSI-3B follows nearly the same overall trajectory. It also climbs during winter, reaches its highest values during approximately the same period, and decreases afterward, although the calculated correlation coefficient between the two curves is only modest 17% to 22%. Their macroscopic shapes appear visually similar. The timing of their turning points, rising phases, and declining phases is largely synchronized, suggesting that trajectory similarity may capture biological relationships not fully reflected by conventional linear correlation statistics. Results discussion: the most striking observation is not the exact numerical correlation but the preservation of seasonal topology. Winter appears to elevate both SBP and TSI-3B simultaneously, producing parallel dome-shaped trajectories. The agreement is particularly evident after smoothing, with a 90-day moving average, indicating that long-term physiological adaptation may dominate over short-term fluctuations. From VPT energy and topological perspectives, the trajectory itself becomes the primary object of study, rather than asking whether one variable predicts another on a day-to-day basis. The more meaningful question may be whether both variables respond coherently to the same underlying environmental forcing, such as seasonal temperature changes, vascular regulation, autonomic activity, or metabolic adaptation. The visual similarity suggests that winter acts as a system-wide stressor affecting multiple physiological subsystems simultaneously. Future work: the next logical step is to incorporate local ambient temperature into the analysis. By recording daily temperature together with SBP and TSI-3B, it may become possible to determine whether environmental temperature directly modulates the trajectory of these physiological variables. Future analysis could quantify onset of winter elevation, rate of seasonal increased peak amplitude, duration of the winter plateau, recovery during spring, total area under the seasonal curve. These topological characteristics may prove more informative than simple averages or instantaneous measurements. The present study documents a clear seasonal winter plateau in both SBP and TSI-Stroke based on existing longitudinal data. During the coming winter, I plan to reside in Taiwan, where winter temperatures are generally comparable to those in Hawaii. In addition to continuing my frequent blood pressure measurements and TSI-Stroke calculations, I will record the daily ambient temperature throughout the season. This prospective dataset will allow direct comparison among environmental temperature, SBP, and TSI-Stroke, providing an opportunity to verify whether the observed winter plateau is consistently associated with seasonal temperature changes and to further quantify their temporal relationships. Conclusion: the overall medical literature generally supports that stroke incidence is higher during winter or colder months, although the strength of the seasonal effect varies by region, climate, and stroke subtype. It is not an absolute rule, but it is a well-recognized epidemiological pattern. Intracerebral hemorrhagic stroke often shows an even stronger seasonal pattern than ischemic stroke, with more cases occurring during winter in several studies. The present longitudinal data demonstrate a consistent seasonal pattern in which systolic blood pressure SBP tends to rise during winter and decline during warmer months. More importantly, TSI-3B exhibits a broadly similar seasonal trajectory despite only modest numerical correlation. The parallel timing of their winter peaks suggests that both variables may be responding to common physiological or environmental influences. These observations support the idea that trajectory analysis and topological similarity may provide additional insight beyond conventional statistical correlation. In this framework, the seasonal winter dome becomes not merely blood pressure phenomenon but a systems level signature of integrated physiological adaptation. The published epidemiological literature has long reported an increased incidence of stroke during winter. My present article does not directly measure stroke incidence but instead demonstrates that both measured SBP and the TSI-Stroke risk warning proxy develop a pronounced winter plateau within the same individual. This observation may provide a physiological explanation for the well-documented seasonal increase in stroke risk. Most epidemiological reports simply state that more strokes occur in winter. My personal data show how the underlying risk profile itself evolves into a winter plateau, providing a potential systems-level explanation rather than merely a seasonal count. That is a somewhat different but valuable perspective. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or published as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C. This content is provided for educational reference only and do not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.